All right, so this mini lecture is going to look at what happens when a wave hits a boundary. And we're going to look at a few different cases of a wave hitting a boundary and what happens to that wave, that energy that's traveling down the medium. We're going to use string as an example of that medium, but this works in all types of waves when they encounter a boundary. So the first boundary we're going to look at is a loose boundary, so unfixed. Now, how might that look on a wave on a string? So let's imagine that we have a string, and we'll just put like an I loop at the end of it, and we'll let it sort of hit a pole, okay? So that pole's going through that I loop, and the string is held horizontally. Now, my question for you, I want you to think about it and kind of predict it, is what if I send a little flick, a wave pulse, down that string? What happens as the wave travels down the string? What happens when it hits this loose boundary? Kind of make that prediction. All right, you can pause the video if you want to think about it a little bit. Okay, so as we imagine this wave traveling and it gets to this ring, that wave has energy. That energy is going to raise this. I'm going to bring it close just so it kind of makes a little closer to that loop. All right. So as that energy hits this ring, you might imagine, rightfully, that it's going to raise that ring up. Well, that's not a whole lot different than if I was hanging onto that ring and I flicked it up. If I did that, what would happen? Well, the wave would be sent in the leftward direction. Similarly, when this wave hits this loose boundary, it's reflected back. So we get reflection when the wave hits that loose boundary. How does it look as it travels backwards? Well, it's as if I had flicked it upright, and the wave travels back unchanged. So we get reflection and the wave is unchanged. It heads back in the same direction that it came. If it was heading in the upward direction when it hit the boundary, it heads back in the upward direction, in the opposite direction, but upward of the medium. All right, so that's a loose boundary. What if instead the boundary was fixed? So instead of having a ring on the end of my string, I just anchor it to a wall. Now what happens? As I send my wave pulse down the string. Okay, so pause the video, kind of think about it. What's going to happen when I get to the end of that, to that wall? All right. So as I approach the wall, and my wave, let's get it closer than that. My wave now hits that wall. The energy, the motion of that wave that the energy is causing a force in the upward direction against that wall. Well, that wall is causing a downward force, Newton's third law, a downward force on that string. Well, a downward force is kind of like if I flicked it in the downward direction. And we find that we get reflection, but the wave pulse is reversed. So we get an inversion of the wave pulse. When it hits a fixed boundary. Both things happen. I get reflection, but with a loose boundary, that reflection causes the wave to remain unchanged. With a fixed boundary, I get an inversion of that reflection. All right, so this is two things that can happen when I hit a boundary. What if instead that boundary is a different medium? So you might imagine that I have two ropes that are attached to each other. And one rope has a different linear density than another rope. Remember, the velocity of a wave is impacted by the tension in that rope and the linear density of that rope. So that's kind of like a boundary. Is it kind of like a loose boundary? Well, it is loose, but depending on whether we're going from a lower linear density to a higher linear density, it might represent more of a fixed boundary. So let's imagine that I have a rope and I'm going into a bigger, knotted, heavier rope. Okay, so I have one rope, I send a flick on this smaller rope that's going to end up hitting this thicker rope. What do you think will happen? Make a prediction. All right. So as I come in, just like previously, as I get close to the boundary, there certainly is an element of looseness to this boundary. It's not fixed. And if it is loose, and this, unlike the wall, this also can have energy traveling through it. It's a new medium. I should get some, this is going to be slightly hard to draw, but you can imagine that this big fat thing, here we'll do this, is going to have a wave going through it. But it's also somewhat of a fixed boundary for this wave. And we see that we get some reflection of the wave. Now, I did not do a good job at making the amount of this happening. So how much energy continues and how much energy is reflected is not well represented here. But two things can happen, which is what I want you to pay attention to. The first is we indeed get some reflection. And we know that the amplitude of that reflection has to be decreased because not all of the energy is reflected. Some of it is what we call transmitted. So we get some transmission into the new medium if that medium can indeed have that energy flowing through it, continue with that wave, so like a thicker string. But it too is not the full amount of energy that the wave had to begin with. Now, how much is transmitted and how much is reflected depends on the two mediums, okay? And that might make some intuitive sense when we've learned that how much energy can flow through a medium is dependent on the medium itself. So we're not going to worry too much about transmission as we move forward. We are going to pay a lot of attention to reflection. I want you to get the idea of the three things that can happen when a wave encounters a boundary. We can get reflection that causes the wave to remain unchanged if the boundary is loose. We can get reflection that causes the wave to be inverted if the boundary is fixed. And if that boundary itself also can allow a wave to pass through it, we get some transmission, some reflection, depending how much of each depends on the two mediums. All right, good job.